I saw this on Amazon, and it was a discount deal for around $18, and I thought why not give it a try, even though I could see a fatal flaw right in the picture for it. I had recently done a video on the cheap 60-watt plus soldering irons from Amazon. I don't know if you've ever tried measuring the temperature of an iron tip with a thermocouple. It can be frustrating to say the least. I thought it would be interesting to compare the temperature reported by this thing against the temperature readings I got with the thermocouple, so I ordered one. There does seem to be a bunch of these. They all look the same, have a big 191 on them and a bunch of different names preceding the 191. I get the big 191 as they are trying to fake the old Hakko tip thermometer. The manual, instruction page is all in Chinese, but shouldn't be needed. The thermometer is very lightweight, but a sturdy enough plastic case. The 9-volt battery is the fatal flaw. I told myself not to buy anything else that uses a 9-volt battery, but this thing was just so cheap. The battery compartment is such a tight fit that the wires have to be pushed into the opening in the case to get the battery to fit with the battery door on. I bet that wasn't even on the instruction page. It comes with 5 thermocouples. They are supposed to be good for about 50 temperature readings each. As with a regular thermocouple, they are polarized. There is a red sleeve on one leg and a blue sleeve on another leg. As I was unable to read the manual, I'm going to go out on a limb here and put the red leg on the post with the red dot and the blue leg on the post with the blue dot, and then the bare leg to the tensioning post that has no marking, just a wild hunch. There is a little rubber disc with a hole in it. There is no sticky side, so I don't think it goes under the sensor. Maybe it's used to try and keep solder splatter out of the movable post. I may have to translate the manual after all. That looks like it's working. Room temperature is not quite that hot, but I've been holding the thermocouple, so that will have its temperature up some. Room is a bit over 80 degrees though. Let me compare it to the Fluke thermometer. I'll let them set a few minutes. Well, that is very close. I don't know how accurate the old Fluke thermometer is. It has to have 30 plus years on it. And if this KD RST 191 lasts out a week, I should probably consider myself lucky. But I have to say, that is a very good start. I think the rubber pad with the hole must be to protect the adjustable post from solder getting down in it. So I'm going to move the rubber pad to below the thermocouple. It should be better able to protect the slot from debris in this position. This is a T15-C1 tip, and I can't remember if it was this tip or the J tip that I calibrated a year or two ago. Of course, I used a regular thermocouple, and it was a bit frustrating. I have the FX951 set to 752 degrees, 400 C. The Hakko instructions are to measure at the center of the plated area. I think I'm pretty close here. I'm thinking it was this tip I used for calibration. That is too close to be a coincidence. This is a T15D12 tip, and I use it more than any other tip. Matter of fact, I would say I've got more hours on this tip than all the others combined. It is reading a little low, say 15 degrees C. It might be time to replace it. It was one of the tips I bought when I bought the station, so 5 to 6 years on it. Amazing how long these tips will last if you have the station set to a fast sleep time. This is the T15D24 tip. It's reading 6 to 7 degrees C low, well within the 10 degree range, and I feel that is a correct temperature. This is the T15D4 tip. It is the largest tip I have for the station, reading about the same as the previous tip. This is a T15-J02 tip. It's the only bent tip I have. Well, now I'm not sure which tip it was I calibrated against. It was one of the small ones is all I remember. The thing is, a small thin tip like this will have a range of temperatures. If I measure near the very tip, it's over 10 degrees cooler. I did read somewhere that the thermocouple would last longer if it was cleaned after use. Now that could be BS, but I guess it's worth a try. As you could see, it is very stable at reading the tip temperature, and I really like that. This works so much better than a regular thermocouple. I should have bought one of these a long time ago. The current price as I'm doing this video is around $22. It works so much better than I expected it to. Even requiring a 9-volt battery is not a deal breaker. I wouldn't feel bad buying this in the $20 to $25 range. It does what it's supposed to do. There is not a lot inside, which is what I expected. 2 screws hold the PCB in place. I tried to find a picture of the inside of a real Hakko 191. Considering Hakko discontinued this thing nearly 20 years ago, I guess I was a little optimistic thinking I would find one. One of the first things I noticed, it looks like I would have easy access to the switch terminals. There is so much room in the case, I think I might replace the 9-volt battery. There is also a voltage regulator IC, even has markings on it, 7530H. So 9 volts is regulated down to 3 volts. Too bad they didn't use 2.5 volts. It would then be so easy. I'll think about it. Could use 3 AAA batteries, but more and more I like the rechargeable solutions. And I am really liking the lithium iron phosphate batteries. Barring something failing, using one of those batteries in a device could very well last the life of the device. The easy and most practical path would be to use 3 AAA batteries. Might even be able to get 3 AA batteries in it. But I bought a couple of these a few years ago, and it's calling to me. It needs to be put to use. Besides the fact every 4 to 6 months I check the voltage on them. If the voltage is much below 3.2 volts, I give them a little charge. Self-discharge is lower than what I was expecting. I think I've only charged them twice since buying them. So this is what I'm going to use to replace the 9-volt battery. This cell's normal output voltage is 3.2 volts. Charge voltage is 3.65 plus or minus 50 millivolts, and maximum charge current is 1.8 amps. For charging, I won't use a standard USB charger. I'm not going to mess with the regulator or reverse blocking diode on the thermometer circuit board, so I'm going to need 5 to 9 volts of output for this. But I'm going to shoot for 9 volts, as I might want to use this to replace a 9-volt battery in anything else. I didn't spend a huge amount of time looking, maybe an hour, but I didn't find a single IC that would do everything I was looking for, at least not for the 9 to 12 volt output. I'm sure there has to be a single IC that has the LI-FE-P04 charge circuit, boost regulator that should go at least to 12 volts, and a cutoff circuit that can be set or fixed at 2.5 volts. If anyone knows of an IC such as this, please leave a comment. I'm interested in finding one. While I didn't find a single package to do what I wanted, I did find a few battery charger ICs that should work. This was one of the simpler ones. It doesn't do any kind of USB battery charging stuff, and that should be fine. I'm going to limit battery charge current to 1 amp. So with any kind of decent efficiency, around 800 milliamps on the USB V-bus line, which means any of the 1.5 amp USB chargers should work fine. Unlike the battery charger IC, that can be narrowed down to 10 or 20 chips to look at, small boost regulators number in the thousands. I picked something I was familiar with. First time I'll be using the TPS 61041, but it is identical to the TPS 61040 except lower power. Now it's still a bit more than I need, but I wasn't going to spend hours looking for the perfect boost regulator. Efficiency chart looks fine for around 1 milliamp, which is what I will need. This is not a new IC, it's been around a while, and certainly a newer chip might offer better efficiency plus other advantages. But this took 10 minutes to pick out, and that included a trip to TI's website to see if there was an updated version of this. There are 2 typical application diagrams in the datasheet, and this is the one I'm going to use. The only difference are these parts here. And this is used to power the device from the V-bus supply in case the battery is dead. The downside is it does increase the leakage current on the battery. By how much, I don't know, but I suspect it would be measured in a few nanoamps. This IC will basically handle all of the charging and control of the battery. One thing it doesn't appear to have is any kind of low battery indicator or cutoff. It has one open drain output for an indicator. It's turned on when it's charging and open in all other normal states. It turns on for 500 milliseconds at a 1 Hz rate for any error it detects. I don't ever want the cell voltage to drop below 2.5 volts and would like a low voltage indicator at say 2.6 volts, so that is something else I'm going to have to add. The battery part of my circuit is taken right from the datasheet. I was going to leave out the thermistor, but I had some 10K ohm thermistors that are now discontinued, so I put it in. Did have to do a bit of math for the R10 and R11 resistors. Since the one I used is discontinued, I left the part number on the schematic for the one the datasheet calls for. For the MOSFET switch here, I'm using a 4.7 megohm as it's the largest value I have. I should order some 10 megohm for spots like this. The power input is a USB-C power-only connector, through a fuse and then into the charger IC. When the 5 volts from the USB charger is connected, the power is supplied to VRun from the PMID pin of the charger IC. Q2 is off from the voltage on the VBus line, and the charge supply to the battery will come from the buck regulator in the charger IC. Now if there is no voltage on VBus, Q2 is on and the VRun voltage will come from the battery. When the mechanical switch is off, the only load on the battery will be the leakage current through the BAT, SW, and PMID pins. Now the datasheet gives a maximum value for the BAT plus SW pins as 1 microamp. I don't think the PMID pin will add much leakage current. It's basically a MOSFET back to the VBus pin. Overall, I'm very pleased with the charger IC. There's an entire family of these chips with different options. Not all of them support lithium iron phosphate cells though. Like the battery charger IC, the boost regulator circuit is taken from the datasheet. I did add an extra filter to the output. It's not needed here, but I included it to do some tests. The voltage divider is set to output 9 volts, and I went with the maximum value inductor listed in the datasheet, 47 microhenry. The feed-forward capacitor here is 1.5 times the starting value listed in the datasheet. I doubt it's near large enough, but it's where I will start. With these values and the about 1 milliamp load, I expect the regulator to burst a few pulses and then pause. That will cause some low-frequency ripple on the output. If it's too large a ripple, I will have to alter the values. I am under the impression that this is a more efficient way to operate the regulator, but I don't know if that assumption is correct. That leaves the rest of the circuit. The switch terminals are going to be connected to the switch in the thermometer. I only have to cut one trace from the switch to use it as the switch for my circuit, a much better looking solution than adding a second power switch. The AT-Tiny microcontroller has one job: monitor the battery voltage. The cell I'm using is listed at greater than 2,000 cycles at 100% depth of discharge, so I'm going to use all of it and set the cutoff at 2.5 volts and probably start the low battery warning at 2.6. I might end up raising that. When the switch is closed, the MCU will start up and check the battery voltage. If the voltage is above the cutoff voltage, the MCU will turn on Q1, supplying power to the boost regulator. Every few seconds, the MCU will check the battery voltage, and when it gets to the level I set for the low battery warning, it will flash the LED. I may even increase the flash rate the lower the battery gets. Really use up its last remaining energy doing something useless. I'll lay out the PCB and get them ordered. The circuit boards arrive, and they look good. I didn't notice I had made a mistake till I had ordered the boards. This transistor is going to turn on very fast. That may be a problem. I will have to test and see. Quite a bit of current will flow into that 4.7 microfarad capacitor. I'm going to populate the battery control section first and make sure it works, that there are no shorts and the charge circuit works. Then I will populate the boost regulator section, making sure nothing is shorted and it's running as it's supposed to be. Then I'll finish up the board, touch up a few solder joints, and then clean the flux from the board. I wasn't even going to use a thermistor, but I had some 10K ohm ones that had been discontinued, so I thought I might as well put one in. I'm going to heat shrink the thermistor right to the battery. I have some 24 gauge wires soldered to the battery tabs, white being the positive terminal. I'll put a shrink wrap sleeve around the entire cell to protect the terminals and hold the wires in place. The shrink wrap extends about 3/4 of an inch over the ends of the cell. That is more for protection while I'm doing my testing than anything else. I'll put the connectors on the wires and that will be the battery pack. I did use a power connector for the battery and a smaller connector for the thermistor. Overkill for this, but why not? There's plenty of room in the case. I need to work on the program for the microcontroller, so I've got to set it up for that. I have the current measurement set up on these switch terminals, so with the boost regulator off, this will give me a good idea of what the microcontroller will pull. The code is set to not turn on the boost regulator, so this will give me the power draw of the microcontroller. A bit over 6 microamps, that's not bad. I'm not sure how accurate that is. Right now, the microcontroller turns on every second and does an ADC measurement. The microcontroller clock is running at 250 kilohertz, so when it's active for a very tiny fraction of a second, it's probably pulling a little under 1 milliamp. I'm happy with that. I've replaced the battery with an adjustable power supply. I want to test how the low battery indicator and cutoff work, as well as see what kind of current it will pull. Here would be the standard operating mode, except there is no load on the 9-volt rail. If there was, I would expect close to a 4 milliamp draw, but I want to test all the other loads. Little boost regulator is not a big power hog with no load. Pulling about 40 microamps total, and 6 of that is the microcontroller. I'm happy with that. It's much less than I expected. That value makes me wonder if I should alter my plans. I probably should skip intercepting the front switch and just let this run on the battery all the time. 1500 milliamp hour battery will run 40 microamps for a very long time. Self-discharge will end up being more than that. I'll think about that. I'll drop the supply voltage and see at what level it starts to tell me the battery is low. Looks like right at 2.6 volts, and it will start to flash the LED. Of course, that LED does take some power to light. As I drop the voltage lower and lower, the LED will flash faster and faster. It takes about 10 seconds to respond to the cutoff voltage level. And I don't think 2.51 volts is going to do it. Next step down will be 2.50. I gave it like 30 seconds at 2.51 and nothing. And there we go. It has shut down. I may increase the levels for low and cutoff. I'll think about that as well. So at cutoff, I'm pulling about 700 nanoamps. That is not horrible. I expect most of that is from the microcontroller. So leakage from the battery controller IC is very low. That should work. One thing nice about the case is there are 2 unused mounting posts. I need a bit more height on the post, so I'm going to install a couple of 440 posts. I will thread the holes in the plastic mounting post with a 440 tab. The plastic is very soft, so I will need to be a bit careful with the post so as not to strip the plastic threads. First, I'm going to drill the hole for the LED to stick through. I can't get the drill and drill bit straight from the inside, so I'm going to melt a pilot hole with this pick. Then drill a hole a bit larger than the diameter of the LED. Now the hard part, making the cutout for the USB-C opening. After getting it marked, I will put a hole at each end to give me a starting point for cutting it out. I'll cut it out with a small burr cutter on the Dremel tool. Not the best looking cutout, but it will do. The screw holes in the PCB are a little oversized, so that gives me a little leeway in positioning the board. Okay, close as I can get it. Not pretty, but only I will notice. I'm going to stick to plan. I'll cut a chunk of trace from the switch circuit. If the microcontroller is always connected to the battery, I would have to do a lot more work on the code. Would need to implement the watchdog timer and all that. This will turn out to be faster. I'll move the 9-volt supply lead from the terminal it was on to the trace I cut from the switch. The ground lead will stay just like it is. I'll solder the switch wires to the terminal that had the positive battery wire and the center lead of the switch. The last modification to the case is to cut out some of the battery compartment to make room for the 18650 battery. I'm using the soldering iron with my tip I use for plastic to cut it away. I'll clean up any plastic that is sticking out. That didn't weaken the bottom of the case much. And the battery door will fit. That should complete case modifications. I'll put it back together and see how it does. When turned on, the LED should give a brief flash and then be off. Well, it's not really showing up well on the video, but it's flashing very fast. It's working, but not like it should. That LED should be off. Here is the gate of Q1, the power switch to the boost regulator. The only time this line should be high is right after the switch is turned on, or if the battery voltage is so low that the controller has entered cutoff mode. The big clue is this part of the waveform. The output pin of the microcontroller is entering the tri-state mode. The only time this pin should be in that state is on reset. Here is the waveform from the power pin of the microcontroller. The voltage is dropping to close to 1.5 volts, well below the minimum operating voltage of the controller. That is because of my carelessness on the design of the power switch to the boost regulator. That cheap switch in the thermometer has quite a bit of contact resistance, and charging the 4.7 microfarad capacitor is more than it can handle. I've got to add a resistor and a capacitor to the circuit. I'll do a little PCB surgery. What I'm doing is adding R15, a 47 k ohm resistor, and C11, a 10 nanofarad capacitor. I think that will slow down the turn-on time of Q1 enough so the mechanical switch isn't seeing a near short when Q1 turns on. After the addition of the RC filter, the voltage to the boost regulator looks like this. So there's a nice gentle 60 to 70 microseconds of turn-on time. I think that will do it. Let me remove the battery number that no longer applies. Let me go over the microcontroller. The one I'm using is the AT-Tiny 412, an 8-pin chip in a nice big package that is easy to work with. In the configuration bits, everything is default except for the frequency select. I have it set to 16 MHz instead of 20. No brownout detect or watchdog timer. For the clock control, I have the prescaler set to 64X, giving me a 250 kHz main clock. The RTC module is set to the 1 kHz clock option. The periodic timer is set to 1024 clock cycles, which should yield a periodic interrupt every 1 second. The RTC timer is set to overflow every 100 milliseconds. The ADC clock divider is set to its minimum, yielding a ADC clock of 125 kHz. It is set to run in standby mode. Initial delay is set to 16 clocks. The positive channel input is set to the internal voltage reference, and the ADC reference is set to the VDD supply voltage. Even though it's not turned on here, the result ready interrupt is used. The VREF module is set to output a 1.5 volt reference to the ADC. To use the 2.5 volt reference, the cutoff voltage of the battery would have to be above 2.9 volts. Only using 2 pins, one to switch the LED and one to switch the power to the boost regulator. Global interrupts are enabled. And again, even though it's not active here, result ready, RTC overflow, and PIT interrupts are used. And finally, the sleep control module. It is enabled and set to the standby mode. There is very little code. These are the ADC result values for the battery levels. Everything is initialized and then startup is called. I turn on the indicator LED, wait for the synchronization of the RTC registers, and then start the RTC module. Then I call to get the ADC results. This function blocks until the results are ready from the ADC. If the result is greater than the battery cutoff value, it is flagged to shut down. The value in the ADC result register is the value of the 1.5 volt reference. So the lower the VDD supply voltage, the larger the reference voltage will read. If the battery voltage is okay, the power is turned on to the boost regulator, and here is where the ADC interrupt is enabled. Then it goes to the main program loop, which puts the controller to sleep. There are 2 timer interrupts to wake it from standby sleep. The 1-second timer checks to see if cutoff count has triggered. If it has, then the controller shuts down. If not, the ADC is turned on and the start conversion command is given. Then it's back to sleep. The 100 millisecond interrupt is used for flashing the LED. It's also used to turn off the power on indicator. The ADC result ready interrupt is where the calculations are done for the battery level. The count values are used to weed out noise at right around the low battery threshold and the battery cutoff threshold. And lastly, the shutdown function. First, the sleep mode is set to power down, then make sure the LED is off, and then turn the power off to the boost regulator. Then the RTC is stopped and interrupts are disabled. Nothing can wake the controller back up except for a power on reset. I've been using the thermometer for a couple of months. It's not something I use every day, but I have tried to use it at every opportunity. It works very well. I'm very glad I ordered it. I should be closing in on 50 tip temperature readings, and it still seems to be reading correctly. I do try to not put any undue pressure on the sensor when measuring the tip, and I clean the flux off the best I can. Only time will tell if that extends the sensor life. I haven't had to recharge the battery yet, and I expect that may be like a every 6-month kind of thing. I'll probably recharge it before the low battery light ever comes on. I enjoyed the small low-power battery replacement project. It turned out better than I expected, and I think with a little work, I could do quite a bit better on the no-load power draw. A project for the future. Thank you for watching.